And so it's my privilege to introduce Yibo Gao. He is from MIT, and he's going to talk to us about the 1/3 to 2/3 conjecture for Coxeter groups. Take it away, Yibo.
Thank you very much for the introduction and invitation. So I'll be talking about 1/3, 2/3 conjecture for Coxeter group. This is joint work with Christian Gaetz, and we are both students of Alex Posnikov. Before I begin, I just want to say that I'm not an expert in the 1/3, 2/3 conjecture, and this talk is really about the perspective of generalizing this conjecture to Coxeter groups. And hopefully I can convince you that this is really a correct generalization. As for the agenda, we'll first introduce the 1/3, 2/3 conjecture, which is still wide open. For the background, we'll talk about weak order and convex sets so that we can generalize the setting to Coxeter groups. And in section 3, 4, 5 here, we'll talk about special cases where we are able to resolve this conjecture. And we are going to end with examples. So hopefully everyone is familiar with these concepts. So here P is a poset on n elements, and linear extension of a poset P is an order preserving bijection from P to the n element chain. We'll let capital E of P to be the set of linear extensions of P, and lowercase ep to be the number of linear extensions of P. For a pair of element PQ in the poset P, let delta PQ be the fraction of linear extensions such that P appears before Q. Okay, so as you can see here in this formula, it is the set of the size of the set of linear extensions where lambda P is smaller than lambda Q over the total number of linear extensions of P. So for example, if P is less than Q, then this delta is going to be 1. And if P is greater than Q in the poset P, then this delta is always 0. And we always have delta PQ plus delta QP equals 1. Right, so the 1/3, 2/3 conjecture says that for any finite poset P that is not a total order, there exists a pair of elements PQ such that this delta is between 1/3 and 2/3. And so if it is a total order, the trivial case, then all of the PQs all of the deltas are going to be either 0 or 1. So the conjecture is not saying anything. So another way to phrase this conjecture, we are going to define the balance constant B of a poset P to be the max over pairs of elements PQ, and we take the mean of delta and 1 minus delta. So this is just to make sure that this quantity here stays below 1/2. So BP is always less than or equal to 1/2. And then the conjecture is saying that the 1/3, 2/3 conjecture is saying that BP is at least 1/3. All right, why 1/3? So this is the prototypical example. This poset here has 3 linear extensions: P1, P2, P3, P1, P3, P2, P3, P1, P2. And you can calculate all of the deltas, and you'll see that they're either 0 or 1 or 1/3 or 2/3. So BP is 1/3 in this case. Okay, so although the conjecture is saying that BP is uniformly bounded below by 1/3, it is already non-trivial to show that it is bounded away from 0. So here are some known bounds. 1/2e by Ken and Lineal, 3/11 by Ken and Sachs, 5 minus square root 5 over 10 by Bradwell, Felsner, and Trotter. So all of these results use some sort of log concavity type argument, like Minkowski theorem or Alexandrov-Fenchel inequality in convex geometry. And there are also some special cases where the 1/3 bound is known. So for example, the width 2 posets the semi-orders, or also the unit interval orders, height 2 posets, series parallel posets. So this one is easy. The last one is easy. So in this talk, I'm going to talk about these generalizations of this with 2 posets, the semi-orders, and some kind of uniform bound. All right. So getting into the background, a Coxeter group W is generated by a set of simple reflections S, where the relations are the SI squares equal the identity for each simple generator, and also Si Sj to the power of m sub ij is the identity, where mij is any positive integer that's at least 2 or infinity. So when it's 2, when mij equals 2, it says that Si and Sj commute. And when it's infinity, it says that there are no relation between Si and Sj. Let L denotes the standard Coxeter length of a Coxeter group element. The left weak order is the transitive closure of this relation W covered by S times W if the length of SW is the length of W plus 1. All right. The reflections denoted by T are defined to be the conjugates of the simple reflections, the SIs. And the right immersion set of W is defined to be the set of reflections such that the length of WT is less than the length of W. So this is a very classical proposition. This is basically what also very related to what I said in the pre-seminar. So W is less than or equal to W prime in the left weak Bruchau order if and only if the immersions of W is contained in the immersions of W prime. So the left weak Bruchau order is exactly characterized by the inclusion of the immersion sets. Right? And standard facts, the length of W is the size of the immersion set of W. Let H be the Hasse diagram of the weak order. We say that a subset of the Coxeter group is convex if for any pair of elements X and Y, in the subset, any shortest length path between X and Y remains in C. So this is a definition of convex sets for any graph, really.
Mind if I ask a question about these groups? Should we be thinking mainly about finite Coxeter groups, or is infinite okay as well?
Here, you can think about any Coxeter group, but in some cases, we'll restrict to the finite ones.
Okay, thanks.
It is still infinite, but I guess in that case, yeah, that's a very good point. The subset C has to be finite, okay. Although sometimes you allow W to be infinite. So proposition by Titz says that any convex set C is of the form where we denote it by W sub A sub B, which is precisely the set of Coxeter elements whose inversion set is bounded below by A and bounded above by B. This is not very hard. For our purposes, because we are going to be considering the size of C in terms of this 1/3, 2/3 setting, we can usually translate this convex set C by some Coxeter group element. So we can assume that usually A is the empty set, or equivalently, you can also assume that B is the whole set of reflections. All right, so finally, an example. The symmetric group Sm is a Coxeter group generated by all the simple transpositions, all the adjacent transpositions, I plus 1. And the reflections are all the transpositions Ij. And Ij is an inversion of W if only if Wi is greater than Wj. And so here is the left weak order on S4. And C being the identity, so this guy, 1, 2, 4, 3, this guy 2, 1, 4, 2, 1, 3, 4, 2, 1, 4, 3, and 3, 1, 4, 2. So this is the square plus an edge. Okay, so like this. You can see that this is convex. And another way of writing this is the set of Coxeter group elements, the set of permutations whose inversions are contained in 1, 3, 2, 3, 2, 4. We'll come back to this example later. All right, so why are we talking about convex sets and what is the relation with the 1/3, 2/3 conjecture? So for a poset P on n elements with some labeling, we can identify the set of linear extensions as a set of permutation because each linear extension is really naturally a permutation. And we'll denote this set by C sub P. And this proposition says that this map from P to C sub P, so from a poset to a convex set in the symmetric group, this gives a bijection between labeled posets on elements and convex sets of the symmetric group. So really, when we're talking about posets, we can just talk about convex sets in the symmetric group. So this is the example that you have seen before. So we have seen this 5 elements, the square plus an edge, as a convex set. And really, these guys are exactly the linear extensions of this n poset. Okay, any questions? All right, and now we are just translating the 1/3, 2/3 conjecture in this language. So recall that this delta is the fraction of the linear extensions where Pj appears before Pi. And in terms of convex sets in the symmetric group, this is the set of permutations where Ij is an inversion of W. So it's even simpler in this description. And this suggests the following definition. So we'll define delta. So here we can let W be any Coxeter group and C be a finite convex set. And for any reflection T here is a reflection, not an inversion. So it's a typo here. Define delta T to be the set of Coxeter group elements in this convex set such that T is your inversion. And over the whole sides of over the sides of the convex set. So this is basically the delta that you have seen before. Where delta is the fraction of the Coxeter group elements in the convex sets that has T as an inversion. And similarly, we can define the balance constant to be the max over all the reflections. And we take the mean of delta and 1 minus delta to make it less than a half. So in this way, we can translate the 1/3, 2/3 conjecture in the language of convex sets. And it seems pretty surprising that the natural generalization of the 1/3, 2/3 conjecture still seems to hold for finite Coxeter group. So this is the main conjecture that we have. Let C be a convex set in the finite Coxeter group where C is not a singleton. So if C is a singleton, this will correspond to a total order in terms of posets where you have only one linear extension. So if C is not singleton, then the balance constant is at least 1/3. And here, the finite Coxeter group part is really important. It has to be finite. So one may argue that for any Coxeter group, or pretty much any Coxeter group, there is a type A2 parabolic subgroup inside it. So maybe the 1/3 only comes from that part, and this conjecture is not interesting. But this is actually not true. So there are genuinely new equality cases in pretty much every type that does not come from the A2 example that you have seen. So I will show you these examples. There's a particularly nice way to think about this problem. One is a finite Coxeter group. So for a finite Coxeter group, we have a corresponding Coxeter arrangement, and a convex set is just a convex set of regions. And the conjecture says that there's a hyperplane that cuts the convex sets, that cuts this convex set into roughly equal parts. So for example, here I have 5 regions, and I can choose this hyperplane that cuts into roughly equal parts. And in this case, the balance constant is 2/5. It's at least 1/3. So for example, this conjecture is really easy when it's a rank 2 root system, rank 2 Coxeter. Okay, so now we are going to talk about some special cases. Any question?
So should it be clear why it's not, why this doesn't work for infinite Coxeter groups if we just take finite convex sets in an infinite Coxeter group?
It doesn't work. There will be examples.
Oh, okay, thanks.
Yeah, I'll show you examples.
I have a question too. I guess since B of C is greater than or equal to 1/3, is that the same as saying that this hyperplane cuts the convex set into roughly equal parts, or does it say more like 1/3, 2/3?
Oh yeah, more like you can always choose a hyperplane so that you cut it and both parts are at least 1/3.
Yeah. Okay.
Yeah.
So that's it. Yeah.
And the intuition is that you want to cut it into like as equal as possible. Yeah, this roughly equal means that within a factor of 2. Okay, so we'll first talk about fully commutative case, and this will correspond to width 2 poset. So an element is fully commutative if no reduced word of W contains a consecutive substring that's Si, Sj, Si with M sub ij copy of it. In this case, we can apply a Coxeter move and change the substring to Sj, Si, Sj. Well, both substrings are alternating, but now you start with Sj in terms of Si. So this is called the Coxeter move or a braid move. So for example, in the symmetric group on 4 elements, this 3, 4, 1, 2 here is fully commutative, but 3, 2, 4, 1 is not. So I think I have shown this example in the pre-seminar. So a permutation is fully commutative if and only if it avoids 3 to 1. And a poset has width k if its longest anti-chain has size k. So you'll easily see that they are a very related concept. So under the bijection between the posets and convex sets that we talked about, width 2 posets P directly corresponds to convex sets C sub P, which equals a lower interval below fully commutative elements in the weak Bruhat order. Okay, so intuitively, why that's true is because if W contains a 3 to 1, then this 3, 2, and 1 will be an anti-chain of size 3. So you will not be width 2 in that case. And pretty much vice versa. So okay, so in this case, we're just talking about lower interval below W in the left weak order, where W is fully commutative. So the 1/3, 2/3 conjecture is known for width 2 posets, and we are going to strengthen these results to other Coxeter groups. The main theorem of this section says that if W is a fully commutative element in any Coxeter group W, whose Coxeter diagram is acyclic, so this acyclic condition is very important, then the balance constant of this interval is at least 1/3. So why do I say W not equal to identity? Because if W equals identity, then it's basically the same case as a chain in terms of poset. So it has only a single element. So in particular, it applies to all finite Coxeter groups because their thinking diagrams are acyclic. All right, so this is an example, or rather a non-example. So the affine Weyl group A3 has this thinking diagram, which is cyclic, which has a cycle. And this element W, sorry. This Weyl group element W S1302 is fully commutative. Well, it has only one copy of every single generator, so you can not possibly do a break move there. But the balance constant is 2/7. So I'll explain this 2/7 later. The proof of this theorem uses the theory of heaps, as defined by Stanbridge. Let S be a reduced word of W. So this heap poset H sub S, so this heap poset depends on the reduced word of W, so not just W itself. And this is the partial order on all of these simple generators inside this word. This is partial order on all elements such that J is less than K if this S sub ij appears before S sub ik, and that they don't commute. And you can see that when you do a commutation move, this heap poset doesn't change. So in the case where W is fully commutative, the heap poset will not depend on the choice of reduced word. And we can write this heap poset just as H sub W. The proposition by Stanbridge says that if W is fully commutative, then the lower interval below W in the left Bruchau order is isomorphic to the lattice of order ideal of this heap poset H sub W. So we can translate this problem for this convex set to some problem on some other poset. So motivated by this proposition here, we have the following definition that's pretty much very similar to what you have seen. So if Q is a poset, we'll let J sub Q to be the order ideals of Q. So this is a lattice. And we define this delta to be the fraction of order ideals that contain X. So delta is like the same delta as before. It's just now it's the fraction of the order ideals that contain the specific element X. And we let B of Q to be the max over X. And we take the mean of delta and 1 minus delta to make it less than 1/2. And in terms of this proposition, in terms of this definition, we'll have the balance constant of this convex set to be like this new balance constant on ideals of this poset H sub W. All right, so here is the previous non-example. So we have W, which is this element S1, S3, S0, S2. And this is the heap poset. So let me just briefly explain why this is a heap poset. So in this poset, you see S1 is less than S0. And that is because S1 appears before S0 in this reduced word. And S1 and S0 doesn't commute. Similarly, S3 and S0 are adjacent in the thinking diagrams, they don't commute. And we have S3 is less than S0, this edge here. Okay, and now what is this B, this new B of HW? So we have 7 order ideals in total, you can count. And the number of order ideals that contain 0 is, there are like 2 order ideals that contain 0, because you have 0, 1, 3 or 0, 1, 2, 3. And by symmetry, you see that all of these B's, all of these deltas is either 2/7 or 5/7. So in this case, the balance constant is 2/7. It is less than 1/3, and it doesn't contradict the theorem because the theorem only applies to acyclic Coxeter diagram. Any questions? Okay, so this is all I'm going to talk about in terms of the proof. I really like this proof because it really shows you why being acyclic is important in this case. And because all the rest of the proofs is just very messy. This one is good. All right, so I'm going to show you some equality cases that's not coming from type A. So the first line here, you'll see the type A example, which is the in terms of poset, it is a 2-element chain and 1-element chain that gives you 1/3, 2/3. And the heap posets, this guy has 3 order ideals. So it has the empty order ideal, where the order ideal contains this element, or the whole poset itself. And this one is in 2 order ideals. The top one is in 1 order ideals. So you have the balance constant to be exactly 1/3. Okay, so this is the type A2 example that you have seen at the very beginning. But we have also very different examples in these other types. So for example, this guy, so D4, where all of these W here are fully commutative. For this to make sense, so this poset has 6 order ideals, and the bottom ones are both in 4 order ideals, and the middle one is in 2 order ideals. So in this case, you can also see the balance constant is 1/3. Also, the same is true for this guy. But I think this has 15 or 21. I kind of forgot, but yeah, this is also gives you the equality. It's exactly 1/3. Oh, by the way, you may notice a slight pattern here, but you cannot actually go further. This is as far as you go. So yeah, so this shows you that you actually have new examples. All right, so moving on to the next special case, we have semiorders. So in the poset world, we said that a poset is a semiorder if there exists a function which like assigns values on your elements, such that P is less than Q in this poset if and only if FQ minus FP is at least 1. So this justifies the name of unit interval, because it says that you can basically put your poset elements on a number line such that you have one is less than the other if their difference is at least 1. And if P is a semi-order, which is not a chain, then the balance constant is at least 1/3. So this is it's not a hard theorem. To generalize this theorem, we are actually going to use the language of root systems and Weyl groups. So this is the axiomatic definition of a root system. We discussed this in the pre-seminar. If this is the first time that you've seen it, it's basically a set of vectors that are really symmetric. The Weyl group is defined to be a finite subgroup of GLE, where E is our ambient vector space, generated by the reflections across the roots. It's a Coxeter group. We can partition phi into positive parts and negative parts. And for such a partition, there's a unique choice of simple roots, such that the set of simple roots is the basis of E, and that each positive root can be written as a non-negative integer linear combination of the simple roots. Here's some new information. So there's a partial order on phi plus called the root poset. That's defined by alpha less than or equal to beta, if only if beta minus alpha is a non-negative linear combination of the simple roots. So by this definition, you can see that the minimal elements of this poset are precisely the simple roots. And there is a unique maximum, so unique maximal element, and this is called the highest root. We'll denote the highest root as C. So this is the root poset of type A. You see that on the bottom, I have the simple root EI minus E sub I plus 1s. And on top, I have a unique maximum, which is E1 minus En. And so let W be a finite crystallographic Weyl group. And we recall this notation, W sub A sub B, which is the set of Weyl group elements whose inversions are bounded between A and B. So we define a convex set to be a generalized semi-order if the inversion set is inside an order ideal of the root poset. It can be written as W sub empty set sub B, where B is an order ideal of the root poset. So why is it the same semi-order in terms of poset? So recall that the semi-order is that you have an F such that P less than Q if and only if FQ minus FP is at least 1. So let's say we have a natural ordering of this poset, then this set of roots, so EI minus EJ, where Fj minus Fi is bounded above by 1. So this is an order ideal in type A sub n minus 1. And so basically there is a direct bijection between order ideals of the root posets of type A with semi-orders, and both are counted by Catalan numbers. You can directly see that the order ideals will correspond to lattice paths in this picture. So theorem of this section says that if C is a non-singleton generalized semi-order, then the balance constant is at least 1/3. And the theorem relies on the following purely root theoretic fact. Well, let me just read it. So let J be a non-empty order ideal of my root poset. Then there exists a simple root alpha inside this order ideal such that we cannot find two different betas also inside this order ideal, such that their reflection, which is still a positive root, is not going to lie in this order ideal J. Well, this is just some fact, which will eventually imply this theorem, but our proof is actually very, very bad. It's really technical and type dependent. Okay, any question?
I don't normally classify proofs as bad. I mean, right or wrong, but not bad. So
I mean, this is bad. Like, I mean, sometimes you have like type independent proof, type uniform proof, and those are really good. Like for example, I think that the theorem that we had in the last section is good because it's completely type independent.
but does that mean your proof is constructive? You put in what type it is, and you put in the order ideal, and you out pops such an alpha?
Yeah, kind of like that. Yeah. All right. Okay, so moving on, we are going to show that there's a uniform lower bound for finite Weyl group, for convex sets in finite Weyl. Yeah, just recall that it is non-trivial that this is bounded away from 0. Okay, so let W be a finite crystallographic Weyl group, and we define the following parameters. There's no need to read those, but those are just some parameters that one can define. Well, actually, let me just say a little bit about this. So I have the highest root C, and if I write C in terms of a sum of the simple roots, so I have coefficients, and this M0 is the smallest coefficient, and M1 is the largest coefficient, and M is just something. And the main theorem says that if C is a non-singleton convex set in W, which is a finite crystallographic Weyl, then B of C is bounded below by this number. E is a natural E. And it achieves, and it's bounded below by 1/2 to the 1/2 times E to the 12. And so this number is not really important here, but it is non-zero. And so this is theorem, and it's really not, it's actually not that bad for the classical types. So in type A, we recover the Canalino result. We basically generalize Canalino's argument. In type A, we get 1/2e. In type BC, we can also get 1/2e, which is not that bad. And in type D, we get 1/2 e to the 4. It's only in the exceptional types that the bound is not
Does
really.
E mean the usual 2.7 something?
Yeah.
Okay. Those numbers look much smaller than I was expecting you to say.
Much smaller?
Yeah, well, 1/2 times e to the 12th.
I mean, yeah, that's very, very small. It's a very bad bound. And also for the exceptional types, you don't need, I mean, because the Weyl group is finite, so you have like a trivial bound of 1 over the size of the Weyl group. So it's really not important.
But the Weyl group is very big.
It's more about the type BCDs.
But is this saying then the 1/3 lower bound is too high?
No. No, it's not. It's just that that conjecture is hard.
Yeah.
That's what it's saying. Okay, any question?
Oh, well, thank you. Let's do our formalities here. Do you mind?
Okay, no, I mean,
okay, are you done or not done?
I'm not done. I still have some time, right? Yeah. All right, so I'm going to talk about.
Mind if I ask about the last slide, the table of results?
Yeah.
Was it unexpected that for E8 you have a better bound than E7?
Oh no, I mean it's. No, these numbers are just not very important.
Okay.
It comes from the fact that you actually divide by this M0, which turns out to work a little bit more in your favor in EA than E7. But these numbers are really not important. It really comes from how the thing is proved.
And you believe 1/3 is a sharp bound for all of these cases?
We still always believe 1/3 is the correct bound.
So and it's not possible that the correct bound is larger than 1/3 for any of these cases?
It's larger than one. No, I mean one can always have some example that is 1/3.
Okay, for each of these Coxeter types.
So I mean there's also this example. These examples. These give you exactly 1/3.
But does that cover all of the Coxeter types in that table?
No, but like for example, EA, you have like E6 as a subgroup, and I mean the 1/3, 2/3 is still wide open. So to classify all the equality cases are just way harder than proving the 1/3, 2/3 as well. So like somehow before proving the main conjecture, we cannot say that these are all the examples. There are still many things that are wide open.
Okay.
So, conclusion. All right, so let's go over the proof techniques here. We are going to use some convex geometry. So let W be a finite crystallographic Weyl group. We have a corresponding Coxeter arrangement, and we define the fundamental alcove to be this simplex. So what this says is that the inner product of V alpha is greater than or equal to 0 for all the alpha in the simple roots. So this says that I'm in the sort of the fundamental region of the Coxeter arrangement. And this affine hyperplane cuts this fundamental region, and it gives you a simplex. So in this way, this alcove is a simplex, it's bounded. All right, so for each Weyl group element, we can define its corresponding alcove by translating the fundamental alcove. And as you may have guessed, for a convex set C, the generalized order polytope is defined to be the union of all of these simplexes. Right, so here's an example. Here we have the A2 Coxeter arrangement. And let's say, for example, this is the, or whatever, or some region is going to be the fundamental region. And you can take some hyperplane, you cut out a simplex, and you just take some union, and you get a polytope. This is B2, you also get a polytope like this. So these are special cases of L-curve polytope defined by Alex and Thomas. Oh, by the way, this definition also should be a definition / proposition because there's a little bit work that you need to do to show that this is indeed a polytope. So this geometric approach to our problem, for reflection T, we'll have H sub T to be the corresponding hyperplane. It cuts the order polytope into two parts, the positive parts and the negative part. And the goal is to show that these two parts have roughly equal volume. By roughly equal, it means that one has the volume sort of within a constant factor of another one. Okay, so the first step, so let C be a convex set, and we let O sub C to be the centroid of this order polytope. Then this lemma says that there exists some T whose corresponding hyperplane is very close to the centroid. And so this inner product just says it's just the distance between the centroid and the corresponding hyperplane HT. And it says that this is bounded above by some number. And so M here is like, it's an absolute constant, and R is the dimension. Yeah, so in other words, there's a hyperplane very close to the centroid, but this is not the end of story because there may still be some bad cases. So I don't think this picture does a good job of what I'm trying to say, but the main point is that there's something more that you need to do. So this is the main proposition. So like Q be a full-dimensional compact convex body with centroid C. Let N be a constant, and V, so think about V as a hyperplane, such that so the centroid is very close to the hyperplane that's corresponding to V. Or here I'm just saying that it's greater than some small negative number. And also these two conditions here says that the hyperplane HB is relatively far from some points in the polytope on both sides. So, or in other words, this hyperplane HB is relatively in the middle of Q. So you have the hyperplane and you have some points that's very far from this hyperplane from one side and very far from this hyperplane from the other side. So as long as we have these conditions, the volume is bounded below by some number like this.
A question, is that bound sharp, or do you think it's sharp?
Oh, this bound is actually okay. Like it's not very bad. It's not. I think it's not completely sharp, but it's not as bad as a comparison to 1/3. Yeah, so our proof generalizes the argument by Ken and Linio, which uses the Brunikovsky theorem. Right, so this Brunikovsky theorem says that, so think about V as a hyperplane, and this Q sub V lambda is a slice by this polytope in the direction of V, and each piece is that labeled by lambda. So this function is concave. And yeah, so this was what this lemma is saying. Yeah, so I think that's all I'm going to say about the proof. So there's something else that you can do in type B to achieve a better bound, but maybe I'll just skip that. It's not so important. Basically, you run the same argument with another polytope that does the same job. But you have different polytopes that can do the same job, but some polytopes give you better bounds than some others. So let me end with some examples. So recall that one of the main theorems says that the balance constant is bounded below from 0 by some absolute constant. But there's no universal bound for arbitrary Coxeter group. It's only for the finite ones, as someone has already asked. So for example, we take Wn to be the Coxeter group whose thinking diagram is a complete graph. Okay. And we take the convex set to be the identity and all of the simple generators. And in this case, all of the deltas are 1 over n plus 1. So all of the deltas are all 1 over n plus 1 or n over n plus 1. And the balance constant is just 1 over n plus 1. So you don't have a uniform bound.
Sorry, so for that example, did it not matter what the MIJs are as long as they're at these 3?
Yes.
Okay.
As long as that. It can be very large, it can be infinite. And in the original 1/3, 2/3 conjecture, it is generally believed that with 2 posets are the ones that come closest to violating the conjecture. But because the 1/3, 2/3 conjecture is still wide open, one cannot really say for sure because it's very likely that nothing violates this conjecture. So with 2 posets corresponds to fully commutative elements. And in this example, we show that this heuristic is not true for fully commutative elements. And the example is also not in finite types. So let W be, let W has this thinking diagram with very high edge weights. Just needed to be high enough. So recall that we have a theorem that says that the balance constant is at least 1/3 for the lower interval below W, where W is fully commutative. So you may expect, because of the previous heuristic, this might be like the 1/3, 2/3 conjecture should hold for this Weyl group, for this Coxeter group. But there is some example where you have a balance constant to be less than 1/3. So the fully commutative guys are not the worst in this case. Okay, so that's actually the end. Thank you very much.
Great, well, thank you for a very nice talk. If you don't mind unsharing your screen, or I could force that.
Yeah, sure.
Great. Okay, now we can clap again so you can actually see us. Awesome. So there were a lot of questions during the talk, but are there any more questions to add? I'm curious about this. I kind of have a question, but it's not well formed yet. I was also looking at this paper of Igor Pak and Greta Panova, and I think there's a third author. They've been looking at this conjecture too. So how much have people studied, like the process of finding a witness pair P and Q that realize the bound?
So frankly speaking, I really don't know much about the frontier of this conjecture. And I don't know what paper you are talking about.
Oh, I'll check out their website actually. And I got a reference out of there too that was useful. Another one of the cases that has been studied is the posets, which are forests.
Oh,
And, yeah, so that's all completely done too.
I see.
Any other questions? If not, well then let's thank Yibo again for a very nice talk.